Okay, vertical dynamics. We're going to be basically doing the exact same stuff we've been doing all this week, except we're going to be looking at certain situations where forces act vertically. For example, an elevator. So using Newton's laws with free body diagrams allows us to determine unknown forces. That we've already been doing. Or acceleration or mass. That you could be asked to solve for any one of those. An object that does not accelerate is in equilibrium. What's another way that we've been talking about equilibrium? Balanced force. Good. So you can rewrite, put a little note there for equilibrium. Balanced force. Okay? Oh, it says it right underneath. But the key there is that F net is 0. And therefore, acceleration is 0. And you'll get these two words thrown at you all the time. Okay? At rest or constant velocity. So, if you are traveling at a constant velocity, you're moving, could there be a force applied? Yes. It's just going to be balanced, probably by friction. Think about like dog sledding. You whip and the dogs go. You get jerked forward and you're going fast, but then eventually those dogs will probably level out with like the sled being dragged by friction, and eventually that dog sled system probably is going to be traveling at a constant rate. At that point, the dogs are applying a force, but there's also a force of friction the other way, and they balance each other out, and you no longer accelerate. There's still a force being applied, but you're no longer accelerating. If you had an ideal situation where there's no friction at all, and I give a ball a roll, I push an object, I give it some acceleration, okay? So for some distance, I accelerate an object, but I no longer apply the force. If there was no friction at all, what would happen to that object? It'll just keep going forever, right? Even though there's no forces. So you can travel without a force applied as well. Being in motion doesn't necessitate a force. Accelerating necessitates a force, though. For all these acceleration problems we've been doing, you look at your data sheet, you got two formulas. F net equals the sum of all forces, and F net equals ma. So what we like to do is put the sum of all forces equal to ma. That's pretty much the goal of every problem. So when an object accelerates, the forces are not all balanced. F net does not equal 0. Therefore, you will accelerate. And that symbol there is capital sigma, and it stands for the sum of all forces. So I'll write that for you. That's what this F1 plus F2 plus F3 plus dot dot dot. Because you could have like so many forces acting. Now for the most part, like in physics 20, it's usually 2. For like a standard question, it's usually 2. And then for like an excellence question that's more difficult, that you'd only get a couple of those on an exam, there might be like 3 forces acting. Or 2-dimensional. Today we're still 1-dimensional, but we're going to go vertical. All right. So I want you to think of like an elevator situation. Basically this picture right here, I just want you to think of a box or a mass, which is essentially a weight, being supported by a cable. You can imagine that in your mind, right? You got a rope, and there's a mass being hung by the rope. Okay? If it's at rest or a constant speed, this diagram at the top left tells you that the support force, which is tension in the rope, is completely balanced by the Okay, so sorry for that. The weight and the tension are completely balanced. Okay? Look at the middle diagram here. The tension force, which is the up force, this is the cable going up. The weight goes down, so you'd have to go the opposite way to hold it up. Like I have to hold it up, right? I hold up. I could feel the tension in the force points up. The weight pulls down. Look at the difference in the size between the red arrow and the black arrow. The W and the F support. Which one's bigger? The red one, right? How much is it bigger by? See that little black arrow? That's F net. It's that simple. Geometrically, it's that simple. It's just a difference. And of course, the leftover force, the net force, is up. So if the net force is up, it's going to accelerate up. You always accelerate in the direction of the net force. Okay, let's look at the third diagram. The weight, the black arrow is quite large. The tension, the F support, is a red arrow. It's much smaller. The net force is the difference between those two. So you'd have leftover force going down. So which way will this guy go? It will accelerate down. If the elevator cable snaps, could you imagine that? There's no longer a tension force. So what's the only force acting on this mass? The gravitational force. So that the only force acts down. So the net force is only coming from one singular force, this one. F net equals mg. What is F net equal to? F net equals ma. The m's cancel, and you will accelerate at the rate of g, which is gravity, 9.81. So this situation here is free fall. You're in free fall. This situation is no different than if you jumped out of an airplane. You're just in free fall. Okay? There's this thing in red that I want to talk about. Can you just turn down your music? There's this thing in red called apparent weight. Anyone hands up, you rode a roller coaster? You rode a roller coaster? Never? If you go up on the loop-de-loop and you're at the top, do you feel anything different in terms of your weight? What about at the bottom of the loop-de-loop when you're picking up a whole bunch of speed? What does it feel like? Does it feel like you're getting pushed into the back of your seat? So that's a feeling of what's called apparent weight. Okay? You actually feel heavier at the bottom of a roller coaster. Or what about when you're on the elevator and you click the button and to go down? What do you feel in your stomach a little bit? Like, you're like, ooh. You feel that? That's only right when you start to accelerate down. And then what happens right when you start to slow to a stop? You're traveling down and then you slow to a stop. You kind of feel like you're being pushed into the bottom of the elevator. You ever feel that? It's like, oh. So that's like a feeling of feeling heavier. We're going to talk about that today. It's called apparent weight. Yeah. Are you talking about the water park? Yeah. Oh yeah? What's that one called? Okay, I want to just show you a strategy for solving these problems, and then we can talk about how to relate this to real life. So, give this a quick read. It's just you're in an elevator and you're going to be being raised up. If you're going to be raised up, which force has to be larger? The up or the down? The up. So then we're going to call that up force T. Okay, T will stand for tension. I'll call it capital T. And then I'll use Fg for the gravitational force, which you guys already have seen before. So in this case, the tension has to be larger than the force of gravity. This is how the workbook provides their solution, so I think I'll relay it to you. Because that force is larger than, because T is larger than Fg, I'm going to make T the positive, and I'm going to make Fg the negative. Just like, it makes sense, because if I drew this picture, T would go up and Fg would go down. But in like, it actually doesn't matter which one you decide to be positive and negative. I always just pick the bigger one to be positive. So in this case, the net force is just T minus Fg. And the reason I put it in that order is because T is larger. I'd rather subtract and then end up positive. I'd rather do that. So the upwards force is 2.7 times 10 to the 4. And the downward force is 2.5 times 10 to the 4. You just throw that in your calculator. Should probably be 0.2. Just do it in a calculator anyway. Okay, so I got 2,000 newtons. So this is the net force acting on the object. The net force is up. Still looking at your guys' quizzes. We're already like almost into November. That's like 2 months of me giving you guys physics teachings, and there's still plenty of you in the room who are forgetting to put directions on vectors. It's troubling. There's not too many of them, and you're pretty much always working with them, except for occasionally not. Velocities, displacements, forces, accelerations, those are vectors. They need direction. This is a one-dimensional problem. The forces are acting in the same dimension, so I don't need any two-dimensional analysis. It's all one dimension. So the net force is 2,000 newtons up. What is the acceleration of the elevator? So on the right side of the equation, you have the sum of all forces. On the left side of the equation, you have ma. To get a, all you have to do is divide out the mass, which is 2550. Okay, acceleration will be this value divided by 2550. We're looking at like 2 sig digs. So the acceleration's 0.78 meters per second square, or newtons per kilo. Doesn't matter which one you use, but typically meters per second square. Yeah, even on your guys' quiz, I saw a lot of people put the wrong unit for acceleration. Some of you put meters per second for acceleration. So like, if you put the wrong unit, I'll probably dock you, because it's like you don't know what you're talking about. You're getting a mark deducted. Units is pretty important, especially if you put the wrong one. Like if you just forget to put a unit, like I might be more forgiving, but if you put the wrong one, yikes. Okay, so what would the acceleration of the elevator in the previous question be in the tension, if the tension, it's a typo, if the tension in the cable was 2.1. So you're just going to go back. what if we change, I'll just highlight it for you with a different color. What if I change this value to 2.1 times 10 to the 4? What's going to happen? You go from being good. You go from having a value larger than 2.5 to a value being smaller than 2.5. So the net force will be down. So then you have to switch gears here. So here, I just actually reorder them. I would just reorder them because in this case now Fg is larger than T. Because the force down is larger than the force up, I'm going to write that one first because it wins. And then my final answer when I calculate it, it'll be positive, but I know it's going down because I'm thinking about the question and I'm not just like relying on like what this equation is going to tell me. I'm thinking. So what's the value for Fg again? 2.5? Okay, so in this case, what's the net force? 4,000 newtons. Now we can write the word down. And to find the acceleration, all I have to do is divide out the mass. What's the mass again? 2550. Okay, newtons per kilo is another way of saying acceleration. 4,000 divided by 2550, I got 1.57. 1.6, thank you, Maria. Times, oh, no, times 10 twos. Correct. Good. And this strategy you guys can use for these problems in general. Like find the force that wins, put that one first as positive. Find the force that works against it and put it negative. Okay, I'm just going to pause the video for a sec. Okay, so for this slide, up force is apparent weight. If the up force is bigger than the down force, you feel heavier. Okay, if the up force is smaller than the down force, you feel lighter. And if the up force matches the down force, you feel the same, you feel normal. All right, we'll talk more about that in a bit here. Let's try to solve some more of these problems. Amran, you mind just grabbing that light? So if the elevator is rising, and you drew a free body diagram for that, what force would point up? Tension in the cable. Does that object have mass? So it has what kind of force acting down? Force of gravity. Do I draw it larger or smaller or the same as the T force? Good, smaller. Why did I draw it smaller? Because it's rising up. Very nice. So then when I write my formula, F net equal to the sum of all forces, in this case there's only two. Which one should I put first? Yeah, I put the bigger one first. They look the same to you? Okay, I'll make it a bit bigger. Ah. How about that? Okay, there you go. Now, what are they asking us to solve for? Very nice. So if I want to solve for t, what do I need to do with that Fg? Beautiful, Maria. So then on the left side, you'd have F net plus Fg equals t. She said you have to plus it out of there, which I agree. What's the formula for F net? MA. What's the formula for FG? MG. Now I want you to think about this left side of the equation. I just want you to think about it in terms of the physics. The tension will equal mg plus the net force. Think about that for a second. What if there was no plus ma? What if it was just T equal to mg? Would it go anywhere? It would just be balanced, right? Now if you add on some net force, you add on some more force, it's going to rise. Okay? And that extra force is based on whatever the acceleration is. Hopefully that makes sense. Like, I want you to think about this diagram. Think about this diagram. This FG would be like this much here, right? See how it matches? See how it matches? What's the rest of this bit then? The rest of this bit, that's the MA. This is the MG. Now look at the equation. Use my pointer. T, that's this big long arrow, is equal to MA, the leftover, and MG, the stuff you just need to match. Like, depending on the mass of the object, the tension, of course, has to be able to match the weight. Now, to get it moving at some acceleration, you have to supply more force. That's the net force, the extra. Okay? So MA plus MG, all we gotta do is punch in the numbers now at this point. 1200, and A and G makes 14652. 14652. Up. Now sig digs is 2. So this is going to round that up. And you got 1.5 times 10 to the 4 newtons up. Okay. How do you guys feel about this so far? Sum of all forces, MA, draw a picture, free body diagram. And like, this is probably the most important thing, the very first equation. Put the big force, the bigger force, positive, and the one that works against it, negative. Okay, and then your net force will be in the direction it's going to travel. Okay, this one's accelerating downward. If it's accelerating downward, which one's bigger? The weight is larger than tension. If that's the case, just put that one first. Because when you subtract them, it'll end up positive in that direction. It must be the same question as before. The same information. 1200 kilograms. Okay, so MA, we have 1200 kilograms at 2.4. And what's FG? MG. So 1200. Actually, before we punch in numbers, I want to do it the same as I did on the last one, so I can explain this to you. Now T goes over to the other side. Are you guys okay with that algebra? All I did was change F net to MA, FG to MG, and then isolate for T in the last step. Negative T on the right becomes positive T on the left. Positive MA on the left becomes negative MA on the right. Now look at this one. The tension has to be smaller than the weight. Why? Has to accelerate down. What if there was no minus ma there? What if there was no minus ma? Block it out of your mind. Then it says T equals mg. Would it go anywhere? So if you want it to go down, you have to have less pull than the weight, right? You need less pull up than the weight. So you'd have to subtract off another term, which is the net force. So this one, compare it to the last one where you had to plus it, right? Look at this was the last slide. ma plus mg. Now this one's mg minus ma. Okay? 1,200 kilos, 9.81 minus 2.4, we're looking at 8892. To 2 sig digs, this is going to round that up. 8.9 times 10 to the 3 newtons. And the tension is an up force. You're solving for the... It's a good question, but no. Because, see how I said right here in the initial assumption that Fg was positive and T was negative? So I've reversed it. Yeah, like your question is really good. What I did up here at the top, I'll just highlight it. This means that the net force will be the direction of the acceleration. So right from the get-go, I know that the net force, because Fg is bigger than T, the net force is going to be what? Down. So if I leave acceleration positive, if I leave it alone, don't do anything to it, this will be down. This will accelerate down. Don't do anything to this. Yeah. Okay, while riding at a constant speed in an elevator, a man has a weight of 670 newtons. What would a scale read if the elevator was accelerating up? Or what about if it was accelerating down? So let's solve this first sentence. Riding at a constant speed. What do you know about that? Balanced, so the down force matches the up force, correct? So how would you write that as an equation? T equals Fg. Okay? How do I know T equals Fg? Because the acceleration is 0. So you'd have F net equals T minus Fg. If the acceleration was 0, then F net is 0. You have T minus Fg. And you can equate them. You can put one of them on the other side. So this right-hand stuff, it's mandatory that you understand this, but you can just jump to this for efficiency. T equals Fg. The magnitudes are equal, the directions are opposite. But understanding that, it comes from this. Okay, so what you can do, if the man has a weight of 670 newtons, okay, that must mean what? In the elevator, he's standing on a scale. At a constant speed, they measure his weight. So that is his actual. His actual weight is 670 newtons because it was read while in a frame of reference where there was no acceleration. It was at a constant speed. So this is his weight because the scale measures the up force, and while at a constant speed it was matched. They matched. So this is his actual weight. So what's going to happen if he accelerates up? What's going to happen if he accelerates down? Let's just make sure you got the physics before we do the calculations. If he's going to accelerate up, he'll feel heavier because the up force is larger. And if he's going to be accelerating down, he'll feel lighter. Okay? So if his actual weight is 670 newtons, you can find his mass. So divide by g and you solve for his mass. .3 kilos. Now because the scale is inside the elevator, you don't need the mass of the elevator. You can just read the scale. For when he goes up, you can use this one. And for when he goes down, you can use this one. So this is when he's traveling. This is when acceleration's up. This is when acceleration's down. Okay, so when you look at the second part of the statement, it says, what would a scale read? What would a scale read? What are you trying to solve for? What does the scale read? Scale reads, careful, the scale reads which force? The up force. The scale reads the up force. So in all these cases, we have to solve for the tension. So in the first column, F net plus Fg will equal T. And in the second column, move the T to the other side and you have Fg minus F net. Okay, so the net force is ma. The mass is 68 times 1 plus the 670. And for the other one, you start with the 670 and subtract the 68 times 1. So this one's 738 newtons. And this one's 602 newtons. And I ran out of space, so who cares about sig digs and rounding or whatever. Is there a lot going on in this problem? Yeah. The key thing that you need to remember here is what a scale will read. Scale measures up force. Scale measures up force. So if you're ever asked to solve for apparent weight, you're being asked to solve for the up force. Question? Down here, yep. Because Fg equals mg, right? And they gave you the weight of a person in newtons. Like in your everyday experience, when you ask somebody their weight, they're going to tell you kilograms, right? But they're actually telling you their mass, right? So in physics, your weight is a force. So if you want to get the mass, you have to divide out 9.81 here on Earth. So this is his weight on Earth. Divide out 9.81, you get his mass. Because F net depends on mass. So you need m. Yeah. Okay, so I'll put a little note for you at the top. If asked to solve for apparent weight, solve for the up force. Okay, and they're going to give you different situations. If you're in an elevator traveling down and then you stop. If you're an elevator traveling up and then stop. If you're an elevator in free fall. If you're an elevator traveling at constant velocity. So that's what your homework, that's what's going to lie in your homework. Okay? Enjoy the section on vertical dynamics because it's a fun one. It's a lot of good force practice, FNAT practice, as well as thinking about various situations.